Hello everyone, thank you for tuning in to my video today. And in this video, we're going to talk about finding a Taylor or McLaurin series of a function. At the end, we're going to do an old AP problem as well to kind of get us in that motivational mood to get ready for our AP test coming up soon. All right, so let's start with Taylor and McLaurin series. Now we've already talked about Taylor and McLaurin polynomials back in topic 10.11. So we should know how to find a Taylor polynomial or a McLaurin polynomial at this point. But a series, now basically is just going to be the summation of that Taylor polynomial. All right, so first of all, the form of a convergent power series. A convergent power series is going to look like this. Okay, when it looks very familiar, it should look like a Taylor polynomial added together each term, right? So we'd say that definition of a Taylor or Maclaurin series, if a function f has derivatives of all orders of x equals c, then the series is going to be basically our Taylor polynomial added together each term. So we call it a Taylor series. Moreover, we talked about this before as well. If c is equal to 0, then the series is called the Maclaurin series for f of x. All right, so let's take a look at our first problem here. It says to find the Maclaurin series in summation form for the following functions, find the interval of convergence as well. All right, so first of all, we have cosine of x. All right, so this is going to be centered at 0, so really it's a Maclaurin series here. We're going to start with our Taylor series form, right? So this is going to be I'll write that down. F of 0, which is cosine of 0, which is 1, right? And then we're going to keep going with our Taylor polynomial. So we have f prime, I'm just going to write these derivatives down here. So f prime of x is negative sine. F double prime is negative cosine. F triple prime is sine. F 4 prime is back to cosine, and it keeps repeating from there, right? So since we're using 0 for this, anything that involves sine is going to be 0, so we're not going to even have those terms, right? So cosine of x is equal the first term, which is 1, plus the second term, which is 0 times something, but it doesn't matter because it's 0, okay? The third term would be the second derivative at 0, which is negative 1, so it's going to be minus 1, divided by 2 factorial times x minus c squared, or just x squared. The third term would again be using sine, so that would be 0. Sorry, the fourth term would be 0. And the fifth term would be using cosine again, so that one's going to be plus 1 over 4 factorial times x minus c to the fourth, or x to the fourth. And you kind of can see the pattern developing here now, right? The next term that we're actually going to have is going to be minus 1 over 6 factorial x to the sixth, and so forth and so on. Okay, and in sigma notation form, we're going n equals 0 to infinity of negative 1 to the n of x to the 2n over 2n factorial, right? Because all we're doing is we're going 2, 4, 6, 8, 2, 4, 6, 8, right? And then we're switching back and forth each time. And the first one would obviously be 0 factorial from that. All right, so we did the first part there, find the Maclaurin series in summation form. That part is done. Now it says to find the interval of convergence. All right, so the interval of convergence, we're going to do the ratio test. So the ratio test says limit, as n approaches infinity, of the n plus first term, so that would be negative 1 to the n plus 1, times x to the 2n plus 2, all over 2n plus 2 factorial, divided by the nth term, or multiplied by the reciprocal of the nth term. So that would be 2n factorial over negative 1 to the n x to the 2n. All right, so then we just need to do some algebraic manipulation here. So let's start with negative 1s. Negative 1 to the n plus 1 is negative 1 to the n times negative 1 to the 1, which is just negative 1. So we have negative 1. And then the x is x to the 2n times x squared over x to the 2n is just x squared. All over 2n factorial divided by 2n plus 2 factorial is going to be 2n plus 2 times 2n plus 1. Everything else is going to cancel out. Remember, the x squared can come out in front of that. So now this leaves me with x squared times this whole limit, except the x is not needed anymore. So off with that. If I put infinity in for n, I would get negative 1 over infinity, which is 0. X squared times 0 is 0, which is less than 1. And that will be true for any value of x will give us a ratio value of less than n. If it's 0, the answer is always 0. It's any value of x will work here. Therefore, our interval of convergence is all real numbers. Or if you want to write an interval notation, like that. Okay, since this will always be less than 1, there's nothing we can do to change that. That means any answer will work just fine. All right, question B, same question here. Find the McLaurin series in summation form for the following functions. Find the interval of convergence as well. So again, C is equal to 0 here for McLaurin series. So I'm just going to do a lot of work here before I even get started with the McLaurin series. I'm going to do f of x equals, I'm going to rewrite this as 1 minus x to negative 1. All right, f prime is negative 1 times 1 minus x to the negative 2 times negative 1. So just positive. So 1 minus x to the negative 2. Second derivative, negative 2 times 1 minus x to the negative 3 times negative 1. So just 2 times 1 minus x to the negative 3. Third derivative would be negative 6 times 1 minus x to the negative 4 times negative 1, so just positive. And let's do one more. So we can really see the pattern here. Negative 24 times 1 minus x to the negative 5th times negative 1. So we have that. So hopefully by now you can see the pattern developing here. Look at the numbers out in front. All right, we got 1, 1, 2, 6, 24. We should recognize that as n factorial. Right, so fn of x is going to be n factorial times 1 minus x, and then the exponents here are just going to be negative, and then 1 higher than what we're looking at here. So negative n plus 1, 1 higher than the derivative. Okay, so with all of that in mind here, let's find at 0. So f of 0 would just be 1. F of 1, sorry, why did I f of 1? F prime of 0 would be 1 over, that'd also be 1. F double prime of 0 would be 2 times that, so that would be 2. F triple prime of 0 would be 6. F fourth prime of 0 would be 24. And really, we can get down to f nth prime of 0 would be n factorial. All right, so now I can write out my McLaurin series. All right, so really we're just looking at f of x equals 1 over 1 minus x. If I was writing out my McLaurin polynomial, right, it'd be 1 plus 1x, or just plus x, plus 2 over 2 factorial x squared, plus 6 over 3 factorial x cubed plus 24 over 4 factorial x to the fourth plus basically n factorial over n factorial x to the n. In other words, 1 x to the n, starting at n equals 0 and going to infinity. So that's part one. The second part is find the interval of convergence. Let's not do any extra work for this. We should recognize that this is a geometric series, right? It's something raised to the power. So let's go back to our geometric series thought process here. Basically, we need x to be absolute value of that needs to be less than 1. So absolute value of x is less than 1. This is our interval of convergence, right? Because this is an infinite geometric series. All right, before we get into our 1 AP problem for the day, here's a table. The following table lists important information about some of the most popular power series encountered in calculus. By most popular, I mean most used. The ones with little hearts next to them, they come up on the BC exam a lot, like as in almost every single year. So if we know those 4 by heart, it'll save us a lot of time when we're doing these problems. Instead of trying to come up with these on our own by using the McLaurin or Taylor polynomials, we just know them and we can jump right to the answer for it. So that will help, save a lot of time in the AP test if you know. If you don't know them, of course, you can always find them. You can always discover them, through the Taylor polynomial. But it'd be really helpful if we just knew them from here on out. Okay? All right, let's take a look at our AP problem. The function f is a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 equals 1, f prime of 1 equals negative 1/2, and the nth derivative of f at 1 is given by the following formula for n is greater than or equal to 2. Write the first 4 non-zero terms and the general term for the Taylor series for f about x equals 1. Okay? So really, we think of that, that's our center. Our center is at x equals 1 there, right? Okay, so let's start here by finding the second derivative at 1, the third derivative at 1 as well. Because we already have the first derivative and the first constant. So now we need the second derivative and third derivative to give us 4 terms. So if I put 2 in for n, I would get negative 1 to the second power times 2 minus 1, which is just 1 factorial, all over 2 squared. Which is just 1 times 1 over 4, or 1/4. And if I, to the third derivative at 2, so it would be negative 1 to the third power. All right, and then 3 minus 1, which is 2 factorial over 2 cubed. So it would be negative 2 over 8, or negative 1/4. All right, so now I can write my polynomial out here, the Taylor series. So f of x equals, and I know f of 1 is 1, right? So 1 plus f prime of x times x minus 1 plus f double prime of x over 2 factorial times x minus 1 squared. One more term. Plus f triple prime of x over 3 factorial times x minus 1 cubed. Plus, forever, but we just want the first 4 non-zero terms, right? All right, so I know I got 1 plus, f prime was negative 1/2, so it's actually minus 1/2 times x minus 1. F double prime was 1/4, so I'm going to write it as 1/4 times 2 factorial. F triple prime was -1/4, so minus 1/4 times 3 factorial. If I want to write this in a different format now, or just a general format here, it would be -1 to the n, right? That's the alternating there. And then n minus 1 factorial over 2 to the n times n factorial times x minus 1 to the n. Okay, now if I want to write that a little, there's another way I can write this. So it's just a different, this is a different route here. These two things are equivalent. If I wrote it like this, 1/4 times 2 times x minus 1 to the second minus, now if I can rewrite this as 1/8 times 3 times x minus 1 to the third plus, now this pattern could become -1 to the n, and that's just 1/2 to the n times x minus 1 to the n. I personally think the second way was a lot easier. It took me a little while to figure out this pattern here. So I like this pattern, the second one, a lot better than the first one. But both are correct. Part B, the Taylor series for f about x equals 1 has a radius of convergence of 2. Find the interval of convergence. All right. So the radius of convergence of 2 means that there's an open interval of convergence is -2 less than or equal to x minus 1 less than or equal to 2. Okay, because I want x minus 1, since we're about x equals 1, it's x minus 1. If I add 1 to both sides, I would get this is my open interval. But now I got to figure out if the two bounds converge or diverge on either end. So this is kind of what we just did recently in one of our previous videos. We're going to do the two bounds separately. Let's do x equals -1 first. And we'll do x equals 3 next. So x equals -1, all right? So we're going to talk about f of -1. So that would be 1 minus 1/2 times -1 minus 1, so minus 2, plus 1/4 times 2 times -1 minus 1, which is -2 squared, minus 1/8 times 3 times -2 cubed, plus so forth and so on. So it would be -1 to the n times -2 to the n over 2 to the n times n. I'm using the second one here. So like I said, I think this one's a lot easier to use than the first one. That's just me. All right. And if we rewrote that as a series, all right, so I'm going to simplify here. So it'll be 1 plus 1, let's see, plus 1/2, plus 1/3, plus, you get the picture here, it's plus 1/n. This is the divergent harmonic series that we already know. So we're not going to include -1 in our interval, okay? Which, based off my knowledge of the AP test, that means x equals 3 probably is going to be convergent. Let's take a look and see. All right, f of 3, they love to give ones where 1 is divergent and 1 is convergent. 1 minus 1/2 times 2 plus 1/4 times 2 times 2 squared plus minus 1/8 times 3 times 2 cubed. And you kind of see where this is headed here as well. It's -1 to the n times 2 to the n over 2 to the n times n. 2 to the n over 2 to the n cancels out. We're left with negative 1 to the n over n. All right, if you do some simplifying with this, you would get 1 minus 1 plus 1/2 minus 1/3. But then, like I said, it's just going to be negative 1 to the n over n. This is the alternating harmonic series. So this one is convergent. So convergent, alternating, harmonic series, which means our bounds are negative 1 to x to less than or equal to 3. Part C, the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. Okay, so f of 1.2, or we can call it P2 of 1.2 is our approximation. So 1 minus 1/2 1.2 minus 1 plus 1 over 4 times 2, 1.2 minus 1 squared. That's 3 terms. So that's it. That's all we're trying to do there. Okay, now we can do some simplifying with that. So 1 minus 1/2 times 0.2 plus 1/8 times 0.2 squared. So that's 1 minus 0.1 plus 0.2 squared. So it's 1/5 times 1/5, which is 1/25 over 1/8. I think that would be 1 over 400. So 1 minus 0.1 is 0.9 or 9/10. So we would get 9/10 plus 1/400. Let's see, that would give me, if I multiply by 40 over 40, 360, 1 over 400. Okay? But I'm pretty sure you could have left it right there. In fact, I don't even know if I did my changing to a fraction complete here correct. Let me see here. Yeah, it looks right to me. Okay, last part here, part D. Show the approximation found in part C is within 0.001 of the exact value of f of 1.2. All right, well, I guess now I really make sure that I did this last part right here. So let me just double check my work before I go too far. 0.2 squared. Actually, let me use my calculator. I did do something wrong. This is 1 over 200. Good thing I checked before I went on to my last part here. Simple math. So then we have 181 over 200. That's better. All right, now I'll show the approximation found in part C is within 0.001 of the exact value of f of 1.2. All right. So we just did our approximation here. So let's think about this for a second. F of 1.2, which is 1 minus 1/2 times 0.2 plus 1 over 4 times 2 times 0.2 squared minus 1 over 8 times 3 times 0.2 cubed. Plus that nth term, which is 0.2 to the n over 2 to the n times n. This is an alternating series, clearly, right? And it looks to be that the terms are decreasing to 0, right? Because the numerator is growing and the denominator is actually shrinking. Or sorry, the other way around. The denominator is growing and the numerator is actually shrinking. So this is an alternating series. I should write this out here. An alternating series with terms decreasing to 0. right? So let's do a limit here as n approaches infinity of the nth term all right, now if I do some manipulations with this, 0.2 to the n, I can change it to 1/5 to the n, but if I can do it better than that, I can do 2/10 to the n. So I can change this as limit, n goes to infinity, of 1/2 to the n times n times 2 to the n over 10 to the n. Why would I do that? Well, obviously then the 2 to the n's can cancel out, and I'm left with limit as n approaches infinity of 1/n times 10 to the n. If I put infinity into that, I would get 1/infinity, which is 0. So now I can apply the alternating series error bound, right? So f of 1.2 minus p2 of 1.2 has to be less than, so absolute value of f of 1.2 minus p2 of 1.2 has to be less than or equal to 1/8 times 3 times 0.2 to the third, which is equal, let's just go 0.2 to the third over 24. So this would be 1/5 to the third, which we can think of as 2/10 to the third. So that would be 2 to the third over 24 times 10 to the third. 8/24 reduces down to 1/3. So I'm left with 1/3 times 1,000, which is 1/3,000. So I want that to be less than this, which is 0.001, which is exactly what we were asked to do in the original part of the problem. Okay, thanks as always for watching my video today. This is on topic 10.14. Only one topic left in Calculus BC at this point. Hopefully we'll see you again next time for that one.